3D room acoustic modelling software. What I wanted to do is give you some guidance when you're starting out using 3D room acoustic modelling software, just to help you avoid some errors or some bad technique in building these models. So what software can we use to build these models? We can use AutoCAD, Google SketchUp, and Rhino 3D are the common software that is used to build the models before they're imported into an acoustic software. The room acoustic analysis software that's commonly used is Acoustic, Ease, or Odeon. When building a model, it is important to build planar surfaces. And what I mean by that, they are flat surfaces or faceted surfaces that are connected together rather than infinite curves. Programs like Rhino 3D have planar surface commands to be able to generate planar surfaces from complex curves. You can also break up curves into equal segments. It is necessary to do this because putting infinite curves into acoustic software can cause very long compilation times of models, and it is not necessary for acoustic purposes to have this level of complexity in your model. When you export a model, it can be time consuming, so make sure it's as simplified as possible. Export curved complex sections with a higher mesh density. What is important in an acoustic model is not necessarily the same in an architectural model. So what we have to do in acoustics is simplify the model for acoustic purposes. A rule of thumb is that any dimension less than 100 millimeters in an architectural model will not be relevant in an acoustic model, and it is better to simplify that architectural model to save on compilation time. Here's an example for you. On the left-hand side here is the architectural model that was directly imported into an acoustic software. And as you can see by the coffered ceiling and by the amount of articulation and detail in the architectural model, this would take a lot of compilation time in acoustic software in the order of days to run. Instead of having a complex architectural model imported into acoustic software, what we can do is simplify the model in Rhino or Google SketchUp, import it into the acoustic software, and apply the same attributes to these simplified surfaces as what's in the architectural model. What I mean by that is we can have a flat ceiling in a geometrical sense in the acoustic model, but what we can apply to that surface is a scattering or diffusion coefficient that simulates the acoustic behavior of what is shown in the architectural model. So the model on the right-hand side here that has been simplified will run in the order of minutes or less than an hour rather than days from what is shown in the left-hand model. Here's a case study for you. It's the 3D computer modelling of a railway station. What we have on the left-hand side here is a long section through the 3D acoustic model of a underground railway station. The grey boxes here are loudspeakers that provide the public address announcement in the station, and they're firing downwards towards the platform area shown in grey here. We have a curved canopy above, which left untreated would provide focused sound reflections back towards people standing on the platform, which would distract them from what they're hearing out of the PA system. The canopy has therefore been treated with acoustic material, shown in brown here, which would capture the first bounce of PA system sound into the canopy and be absorbed. Also, on the left and right of the platform where the train pulls in, we have acoustic absorption at low level. This is to absorb train noise as it comes into the station and reduce the possibility of excessive reverberant noise level in the train station. On the right-hand side here is an output from the computer model. What we have is the C50 or the clarity index for speech, mapped over the whole floor area. The desirable C50 or clarity is 0 or greater dB. And what this basically means is that for a clarity index of 0 or greater, it enhances the sound by 1 or 2 dB. A clarity index of -2 means it detracts from the clarity of the sound within the railway station area. As you can see here, with downward firing loudspeakers, we get a clarity index of 0 to 1 over the majority of the concourse area. The areas where we don't get a good clarity index, which is -2, is in the transfer area between the concourse area and another area of the station. And this was an area where there were no loudspeakers located in the ceiling. So it is therefore quite understandable why we would get a low clarity index. To rectify this, loudspeakers were added in the ceiling of that transfer area between the station areas. And just to finish off this section, here's a picture of the station in construction to show you the absorptive panels in the cavity and also those absorptive panels I talked about on the sides, which were to absorb train noise as the trains come into the station. Here's another example of acoustic computer modelling for a train station, and this is in escalator areas where people were walking down from the entrance to the station to the platform areas. It shows loudspeakers located in the escalator cabin with proposed acoustic treatment on the ceiling. This was quite a difficult space to provide intelligible PA announcements because it was a very tall space and we had limited locations to locate loudspeakers to provide the public address announcement messages. What we ended up doing is locating the loudspeakers on the wall areas and then 2 loudspeakers in the ceiling at the top of the escalators. The only areas we could provide acoustic absorption was on the ceiling, which at first glance might seem quite distant away from where the occupants of the escalator or the occupants of the station might be going down the escalator. Here's an output of the direct sound pressure level at head height on the escalators from the loudspeaker system. We have the loudspeakers, which are shown here as A0 to A5 and B0 to B5, located in a plan orientation. The direct sound pressure level is shown to be between 80 and 86 dB across the majority of the escalator cabin here. What we can deduce from that is that we're getting quite an even dispersion of sound across the escalator cabin, which is desirable. And just to finish off, here is a picture of that finished escalator cabin showing the loudspeakers located on the sides there.